Section 12.6, Cylinders and Quadric Surfaces. The curves of intersection of a surface with planes parallel to the coordinate planes are called traces, or cross-sections of the surface. A cylinder is a surface that consists of all lines, called rulings, that are parallel to a given line and pass through a given plane curve. So as an example, let's sketch the graph of the surface z equals x squared. Notice that in the xz plane, not in 3D, this is just the parabola, z equals x squared. You could think of it like y equals x squared, except that it's z instead of y. So notice there is no restriction on y. So we can move this parabola along the y-axis. No matter what value of y there is, it'll be the same parabola. We can move it infinitely backwards and forwards, so we get this kind of parabolic shape. Let's see if I can draw it. Oops. So something like, let's see, something like this. So the end should be roughly parabola shaped. Hopefully yours looks a little bit better than mine. And we need to put in an axis, so how about we do that right over here. It should be in front of that back part, but it should be behind this part. But we put in our x and y axis too. So here's the origin 0. Okay, so notice that at the ends we have parabolas, but there aren't really any ends. This continues infinitely to the left and to the right, or infinitely along the y-axis. And notice there's parabolas all along the way, so there's a parabola right over here also. That's our z equals x squared parabola in the xz plane. But there's also parabolas everywhere, because this thing is a parabolic cylinder. You might be saying, well, why is it a cylinder? Well, if you were to take another color, how about this one, and draw rulings, then you would see that you can build the cylinder out of rulings that are all parallel to the y-axis. And since a cylinder is any surface that you can build up out of these rulings parallel to a given line, that makes this thing a cylinder, even though it doesn't look exactly like your classic cylinder. But if you were to draw enough of these, lines, these rulings over here, then you would build up this entire curve, or this entire surface. How about we do another example? Oh, by the way, notice that we're missing the y variable over here. Anytime that you're missing a variable in your equation, you're gonna end up with a cylinder. So notice in these two, we're missing over here we're missing z, so it's gonna be a cylinder, and over here we're missing x, so that's gonna be a cylinder. But they'll look a little bit different. Notice in the xy plane, that's a circle. So z can be anything. So no matter what level we are on the z-axis, it's still a circle. So you could think of it as an infinite stack of circles, just like the previous example was an infinite stack of parabolas. So that just ends up becoming our classic circular cylinder. I think my drawings get worse and worse. So it looks something like this, and I'll throw in a z-axis, and I'll throw in y-axis, and an x-axis. There's the origin. And notice we can draw rulings. In this case, all of the rulings are parallel to the z-axis. Okay, so it's not built up of parabolas, it's built up out of circles, so this is a circular cylinder. Our radius is 1, because x squared plus y squared equals 1. And our axis in this case is the z-axis, because that was our omitted variable. So notice in the next one we're missing x. So we expect that our cylinder will be kind of built around the x-axis. So let's try drawing it with that perspective in mind. So it should look something like this. Maybe I want to get a little bit closer, let's see. I'm just not happy with the way that these lines are coming out. Probably looked even better before, actually. But here's my z-axis. Here's my y-axis. And here's my x-axis. Then I could draw rulings. And notice those are all going to be parallel to the x-axis in this case. Okay, so that's again a circular cylinder. Our radius is still 1. However, our axis is now the x-axis. Remember that this is infinite on the top and bottom. So is this, infinite. I'm just drawing a slice of the cylinder, basically. Similar to conic sections, we have quadric surfaces. They're just graphs of second-degree equations in 3 variables instead of in 2 variables. So the most general such equation is this mess, but that involves translations all around the plane. What we'll do is we'll just consider equations in these forms, and then we'll translate them later if we need to, and make them more complicated. This is just what you get when you do x minus something and then square it, and then you distribute everything out, or y minus something, etc. So as an example, let's use traces to sketch the quadric surface with this equation. Remember that rulings were lines parallel to a certain line that you build up your cylinder out of, but traces are just slices. So let's see if we can identify some slices of this thing. Well, if we were to slice in the xy plane, that would mean z equals 0. So that slice would correspond to x squared plus y squared over 9 equals 1. Okay, well that's just an ellipse. So it looks like, in general, if we slice at any constant z value, we should get x squared plus y squared over 9 equals 1 minus that constant squared over 4. So that'll still be an ellipse, because I could just divide by 1 minus k squared over 4 on both sides and set it equal to 1. This is all assuming that k is between minus 2 and 2, of course, otherwise this thing wouldn't even be defined, because this thing can't be negative. So what if we slice in a different plane? How about I slice where x is constant? So then we get y squared over 9 plus z squared over 4 equals 1 minus k squared, so that's just 1 minus constant squared, so that's still an ellipse for the same reason as before. It's just an ellipse in the yz plane now, instead of the xy plane. if I slice with y constant, then I end up with x squared plus z squared over 4. And that's just going to be 1 minus k squared over 9. So it looks like no matter how I slice, I should get an ellipse. These are all ellipses. So I think I should get some kind of like a blimp looking thing. Let's see if I can draw it. Something roughly like this. And if I slice right over here, then it's a nice ellipse. So I can put my z-axis right over there. How am I going to do this perspective-wise? I guess I'll make the x-axis come out like that. And we'll make the y-axis come out over here like this. Notice that it doesn't matter where I slice, I'll still get an ellipse, even if I slice horizontally. Still an ellipse. And those are our traces. Alright, so here's the origin right over there. So over here would be if x and y are both 0, so that makes c equal 2. Over here would be if x and z are 0, so y is 3. And over here is when y and z are 0, so x is 1. And we call this an ellipsoid because all of the traces are ellipses. Alright, let's use traces to sketch z equals 4x squared plus y squared. So again, how about we set one of the variables equals 0, how about x is 0? Because then you just get z equals y squared. So it's an obvious parabola in the yz plane. So again, in general, you could just now set x equal to some constant and see that it's just going to be a parabola in the yz plane because adding some constant doesn't change anything. Okay, so what if I make y equals a constant? Well, then still we have c equals 4x squared plus a constant squared. So that's still a parabola. So it's a parabola in the yz plane and in the xz plane. How about if z is a constant? Well, then we get 4x squared plus y squared is a constant, which we recognize as an ellipse again. So it looks like in the yz plane and xz plane we have parabolas, but in the xy plane our slices are ellipses. So I should get some kind of bowl shape. Let's see if I can draw that. Roughly like this, where my slices going straight down should all be parabolas. So it doesn't matter where I slice, I should get a nice parabola. If I slice over here, it should be a parabola. And even over here. But notice that if I slice horizontally instead of vertically, that should be an ellipse because that's our xy plane. Imagine projecting that down. No matter where I slice horizontally, it should be an ellipse. So how about I put my z-axis right over here. And then I can put my y-axis over here and my x-axis over there. And here's the origin. And we call this an elliptic paraboloid. It's like a cross between parabola and an ellipse, but also 3D. How about the surface z equals y squared minus x squared? Again, let's set one of our variables equal to a constant so that we can get cross-sectional traces. So we could set x equals constant to see what happens in the yz plane. Then we'll get z equals y squared minus k squared. So if I were to draw this family of curves, then notice that they are all parabolas. So that we get this parabola when k equals 0. We get something like this parabola when k is plus or minus 1. Doesn't matter because we're squaring it anyway. And we get something like this parabola when k is plus or minus 2. Remember that our variables are z and y. X is constant, so we are in the yz plane. Then I could set y equals constant, and I could see that I get z equals negative x squared plus k squared. So that means that these traces are all parabolas, but they're negative parabolas. So like here's the parabola for k equals 0, and then here's the parabola, say, for k equals plus or minus 1, and then say that's the parabola for plus or minus 2. Hopefully yours are more symmetrical than mine. And we're in the xz plane now. Okay, what if z is constant? Well, then we end up with y squared minus x squared is k. So those aren't ellipses because of the minus. They're not parabolas because both the variables are squared. So those are hyperbolas. Notice that if k is 0, then we just end up with y equals plus or minus x, so those are just these lines. So that's at 0. But if k ranges, let's say k equals 1, then we get a y squared parabola, so y is first, so that's vertical. So this is it. K equals 1, something like that. And if k equals minus 1, we get horizontal parabolas because it just switches the order when we make a minus. Instead of y squared minus x squared, we get x squared minus y squared. So let's try drawing this. Let's see. We could see that we're going to have this kind of parabolic shape. So something like this. And that's if we're slicing over here where x is constant. So that's our yz plane. And if we slice the other way though, it should also be parabola, but it's kind of like twists a little bit. So let's see if I can try drawing. Should look roughly like this. Where if I slice over here, I get these parabolas. And then if I were to slice in the xy plane like that, notice I get hyperbolas. So how about I draw a little bit behind it so you could see? This is basically just like a saddle shape. In fact, later on we'll look at saddle points, but for now I guess it's just a little teaser. Okay, roughly like something like that. So here's the z-axis. Where should I put my y-axis? How about over here? And I'll put my x-axis over there. So here's the origin. I should probably indicate, there we go. Okay, so this is called a hyperbolic paraboloid, because we got some parabola cross sections and some hyperbola cross sections. How about the surface x squared over 4 plus y squared minus z squared over 4 equals 1? Again, we'll set one variable equal constant. We'll see what traces we get. So x squared over 4 plus y squared equals 1 plus k squared over 4 is what we get when z is constant. And notice that that's just an ellipse, because we got the plus and both are squared. If we've got y equals constant, then we've got x squared over 4 minus z squared over 4 equals 1 minus k squared. So that's a hyperbola again. If x is constant, then we get y squared minus c squared over 4 equal to 1 minus k squared over 4. So another hyperbola. So it looks like this is a family of ellipses for different values of k, and this is a family of hyperbolas for different values of k. And of course I messed that up. There we go. So we should get slices horizontally that are ellipses and vertical slices that are hyperbolas, so we need to kind of twist it vertically, but make sure that it's nice and round horizontally, roundish. So you get this kind of like drum-like shape. So here's like a hyperbola slice. And another little slice. And if I slice this way, then I get an ellipse. So I'll put my y-axis over there, put my x-axis over there, and my z-axis. And how about I connect these? Okay. So notice that if x and z are both 0, this will be the point 0, 1, 0, if we want to add a little more detail. And similarly, if y and z are 0, x is 2. Okay, so we have some hyperbolas, we have some ellipses, but not many. It's mostly hyperbolas, so we call this a hyperboloid of one sheet. We say one sheet because it's one piece that's all connected. So let's take a look at a couple different potential surfaces that we can have. These are basically all our possibilities, assuming that we're centered around the z-axis. If we're centered around a different axis, you just replace the z variable with whatever axis you want to center around. So it makes more of a difference for something like the elliptic paraboloid, where the axis pokes out at it. So if you wanted an elliptic paraboloid around the y-axis, for example, then you would have a y without the square. So notice that there's a couple, there are a couple patterns here. If you have everything positive equaling 1, everything squared, then you just have an ellipsoid very similar to your ellipse in 2 dimensions. Whereas when you start throwing in a minus sign or a second minus sign, then you end up with a hyperboloid. Just like in 2 dimensions, if you change the plus to a minus, you would get a hyperbola. If you don't square one of the variables, then you get a parabola, just like y equals x squared parabola. Whereas if you don't square one of the variables and you subtract also, then you get a kind of hybrid between a hyperbola and a parabola, so it's a hyperbolic paraboloid. And then the last case is a cone. It's just like a parabola, but instead you end up squaring that z variable, so then you end up with something underneath also. So let's do an example taking advantage of our new table. Notice that if we take this equation and we move the 4 over to the other side, so we get minus 4, and then we divide by minus 4, we end up with minus x squared plus y squared over 4 minus z squared over 2 equals 1. So we have everything squared and 2 minus signs, so let's go back. Oh, well, there you go. Hyperboloid of 2 sheets. 2 minus signs, 2 sheets. If it was 1 minus sign, it would be 1 sheet. So we already know what this thing is. So we should be able to draw it. Notice, however, that the axis is different. In our table, we have the z getting the plus sign. So it's centered around the z-axis, but in our example, we have the y variable with the plus sign. So that means that our axis shifted, and our axis is now the y-axis. So we can draw it pretty much the same way, we just have to draw it centered around the y-axis. So how about we try drawing our two little bowl-like things. Try to point it a little more. Wow. Really not coming out very good, but that's okay. And it's 2 sheets, so I should get 1 more of these. Something like this. Okay, so if I slice horizontally, I should get hyperbolas now. Okay, let's put in our axes. So I'll throw in a z-axis in between them, and I'll connect them using the y-axis because they're centered around the y-axis. So the tip of this guy should have been over there, but that's okay. It's close enough, at least for me. Hopefully yours is better. Maybe you can, erase, take your time. But in any case, I think it's hopefully kind of clear what it looks like. Okay, so it looks like for this one we have to complete the square because we have some extra terms getting in the way. Okay, so we complete the square, we'll end up with y minus 1 equals x minus 3 squared plus 2z squared. So instead of x squared, we have x minus 3 squared, and instead of y, we have y minus 1. The y is not squared, so we know this thing's going to be a paraboloid, but this is a shifted paraboloid. Also notice that there's a plus, so it's an elliptic paraboloid, not a hyperbolic. Okay, also, we don't have z, we have y. So that means that our axis would be the y-axis, except that it's shifted. So the axis will be parallel to the y-axis. So let's just make a note of that. Our axis will be parallel to the y-axis. It'll just be shifted by 1. So our vertex will also be shifted. It won't be at 0, 0 anymore. It'll now be at 3, 1, 0. So let's try drawing this. We have our elliptic paraboloid. I'm drawing it horizontally now because its axis is parallel to the y-axis. And I'll draw the axis a little bit farther away. So here's z, and here's y. and then here's x, and here's the origin. Okay, so that means that still if we slice it, we get these nice parabolas over here, and obviously we get ellipses if we slice vertically. And our vertex is at 3, 1, 0.